Thank you. Nice to meet you, everyone. Thanks for the intro. So my name is Maria. I work at Purdue. I've been here for a while, and wrapping up my dissertation in this topics of, how to connect these two ideas of deep learning and symbolic models. And I'll kind of like give you a motivation, an overview of to like why natural language and why discourse for this kind of tasks, and then a little bit of like how we go about modeling this kind of things. When we are all familiar with deep learning and the craze around deep learning for NLP particularly, and we have to recognize that deep learning methods have made impressive advancements in just a few years. So we had in the 90s all of these NLP tasks that several baselines, part of speech tagging, semantic parsing, semantic role labeling, and just introducing neural nets were able to advance all of these performances across all of these tasks. And then particularly large scale language models were able to take advantage of like huge amounts of data that we have for free in the internet to be able to kind of model patterns of language that emerge, right? And they have been very impressive demos, right? Of putting, in this case, this is GPT-3, particularly an example of GPT-3 in action, just answering a question in natural language and given, a seemingly, impressive response to come from a machine learning model. The way these models works is that they try to map inputs to outputs while encoding the structure in what we call a hidden high dimensional space. So basically, a set of mathematical computations and nonlinearities that are built on top of the initial representation and then train on a particular task. In the case of language models, is usually learn to mask certain words in the sentence and learn to predict them, or learn to predict the next sentence in a paragraph. And this way, they learn to capture, kind of like what words go together in what context to kind of learn language patterns. However, I mean, there are drawbacks, in these types of approaches. On one part, they're really hard to train. The space of parameters that are used in these models as they've been introduced, it's like it had exploded exponentially. So you had BERT, in 2018, I think it was released, was already, a very big model in the billions of parameters. And then GPT-3, it's in the 180 billions of parameters. So not everyone can train these models, right? You need a lot of resources to do it, and they need massive amounts of data. So this has two drawbacks, right? On one part, well, you need to have this data, but then also you can't curate it, right? So anything that's in the web ends up being fed into these models. And there's been a lot of talk recently, about biases or where certain like patterns emerge that were just picked up. There's also, a lot of work recently on looking at, what these models can and can't capture. And they've been shown to show like they are not consistent predictors, right? You can, sometimes get behavior that it's unexpected. They make shallow statistical associations. So you might think that, oh, I'm making a very big very good performance in this particular task. But when you really look into it, it might be picking up some like spurious patterns in the data and not really, solving the task that they aim to solve. And then they're also unexplainable black boxes. So we don't know what kind of associations are going in there. So they have this like attention layers where they try to look at, co-occurrences and how two things are likely to be predicted together. But other than that, it's like really hard with all these layers and all these parameters to know exactly what is being captured now. On the other side, there's like this other line of work that used to be what was in, at the beginning of AI in the 70s, where we were thinking about AI and inferences of building this like massive knowledge bases that represent the knowledge of the world. And we have explicitly modeling, entities, relations, and facts, and then, running inference procedures on top of that to be able to discover new facts. So the go-to example is like, if we know that all people are mortal and we know that Socrates is a person, then we are be able to infer things like, well, Socrates is mortal. It's a very natural way to express and reason over problems because it's very akin to the way we humans, kind of like model knowledge and make inferences. And a lot of work throughout the decades has been done on learning models from data, symbolic models from data, and dealing with uncertainty. Uncertainty means, well, some of these facts might not necessarily always be true. There's like some probability assigned to certain facts occurring together and so on. And there's a big body on work on statistics and computer science on trying to model this uncertainty. This is where the term probabilistic graphical models comes into mind. And the idea of these models is to kind of like explicitly model dependencies between different decisions. The downsides of these types of models is that they're less expressive, right? They're less expressive than neural models because, let's say, if we wanted to assign one symbol to every type of word form in the English language, and then all possible dependencies, then the space starts to explode, right? So that was one of the motivations for distributed representations in neural nets. It's harder to cover the high dimensional noisy space, and it's also pretty sparse, right? If you were to represent the whole word, there's a lot of like sparsity in your representation. So, searching over it, it's expensive. Explicitly modeling is expensive. So that's kind of like the downside of this model. So we have, highly interpretable, easy to manipulate, easy to inject domain knowledge, but less expressive and hard to compute. And then we have neural models that are, well, very expressive, can work with huge amounts of data, can model the noise or be robust to the noise, but I mean, we have no idea what's going on inside them. So before I jump into, kind of like this hybrid space of how to bring these two things together, I wanted to give a little bit of background on what I mean when I'm talking about probabilistic inference and some concepts that are going to come across. So probabilistic inference is the task of deriving the probability of one or more random variables taking a specific value or set of values, right? So it's like, what is the likelihood of these things happening? And a factor graph is particularly one type of probabilistic graphical model or way to express a probabilistic model in which we explicitly model things as a graph. So the nodes in this graph are the variables. They can either be evidence if they're known, or they are going to be query or predicted if they're not known. And then factors are other nodes that connect these variables as them having a dependency. So let's say that I'm going to say maybe the value of A depends on the value of B, then I can have a node that represents the dependency between these two things. So factors can be connected to many variables. It can be 2, 3, or more. And they usually come with a factor function. A factor function is basically what defines what is the relationship between these variables. So you could model things like an implication, right? So A implies B, but it can be, many things. In factor graphs, usually each factor is tied to a factor function that is going to be used to score kind of like the likelihood of that relationship happening. We're going to call the weight. And it describes, the influence that the factor has on all the variables involved in it. And then once we have a full factor graph, we have basically a possible world, right? Which is every type of assignment that you could have in the factor graph. So you have all these weights, and they are not equally probable, right? So you have some instances of this world that are more probable than others. And usually probabilistic inference looks at, trying to quantify these probabilities and try to find, let's say, maybe the most likely assignment of things happening at the same time. So we move from like, oh, I'm just trying to predict this one thing to, oh, I'm trying to predict all of these things at the same time and how they interact with each other. If there are any questions right now, just feel free to jump in. Okay. So we're trying to look at, how do we get to the best of both worlds, right? So we want to be able to combine the strengths of both paradigms so that we can reason over rich neural representations, but at the same time be able to make symbolic abstractions over them. So think about, we would like to, let's say, maybe explicitly model a particular concept, but then this concept can have a distributed representation of what this concept is. And we pitch in this work that the perfect candidate for a hybrid approach is analyzing natural language discourse. And why is this? So when we talk about discourse in linguistics, we usually mean dealing with one or more snippets of text, right? So we are not looking at just words in isolation. We're not looking just at sentences in isolation. We're looking at maybe pairs, triples, paragraphs, documents. So there's tons of different language units that are here that kind of flow together to convey meaning. There are structural dependencies between them. So let's say we have a conversation, right? So a conversation there usually involves some back and forth. So whatever I say provides a context to what you're going to take into account when you reply. So that's one type of structural dependency. Another is like how people construct arguments, right? So people, make a claim, then provide, a supporting argument to either support or attack that claim. And then we also have the broader context, right? So language doesn't occur in isolation. So who is the person talking? What's their background? Who they're talking to? What's the intent? All of those things, come into play when we analyze discourse. So in this talk, I'm going to focus a lot on social context because this is the area that we work on. But this is generally, applicable to other types of context. So let's say that you're there's an image or like a physical space surrounding the language event. That's also some type of context, or prosody when you're talking about speech. So what is it about this course that makes it so challenging? So I have here an example about a debate, going on between the two vice presidential candidates last year, discussing the topic of abortion. So, they come here and Vice President Harris talks about women, poor women, women of color, to emphasize the negative aspects of prohibiting, abortion policies towards these groups. But on the other side, then Vice President Pence comes in, and then he talks about the negative impact of permissive abortion policies for the unborn children. So we have, two people talking about the same thing, but putting the emphasis in different types of entities, right? And on different types of arguments around these entities. So this is a very challenging domain because we're talking about a lot of concepts that are difficult to model and identify. So we have the entities, we have the sentiment towards them, we have the issue that we're discussing, who these people are, the party they belong to. All of these things come into play into kind of like mapping out what they're saying and try to analyze this type of interaction. So our goal is to build neural-symbolic models that can integrate expressive textual representation. So we don't want to say, oh, all of this work that's been done on BERT and GPT, it's useless, right? We know that there's some value there as to representing language that we want to be able to leverage. But at the same time, we want to be able to support what we call structure prediction across long text. This means, well, I'm not predicting just one variable, right? I'm predicting all of these things that connect together. And then also, we're going to be able to combine several modalities and the representations. When I mean modalities, I mean, well, maybe I want to represent text and what it means to talk about children, what it means to talk about women, but I also want to be able to represent maybe social concepts, right? Who is this user? Who does this person relate to? What are there other people in their party that interact with them? So to provide kind of like a wider context. And then explainable, right? So that's the call to fame and symbolic model. So I'm going to be able to include some symbols here to explicitly reason about concepts, and then being able to kind of like know what's going on behind the hood in my model. What am I modeling? What is being activated? To sort of understand the predictions that I'm making and why. And then lastly, let us instantly introduce domain knowledge. So it's great that we have tons of data that we can get for free, that we can learn from, but sometimes I want to be able to explicitly teach my model certain things. So if you're making this mistake, or I know this thing about the world, I want to be able to, explicitly model it so that my model can, work with it. So I'm going to cover kind of like what's out there right now in these spaces, and then how our work kind of like ties into this. So there are a lot of frameworks that provide languages to express graphical models. When I say graphical models, it's this kind of like, factor graph, probabilistic inference that I went over before. So there are already, there's been a lot of work in this. There are a lot of frameworks that provide you a language to express these types of graphical models and explicitly model them and then reason over them. There's Markov logic networks on one side, probabilistic soft logic. I won't go into the details, but if you're interested in this kind of work, these are the two things to look into. So what they do is they provide a logic language to express these types of interactions. So you have the world here. In this case, they're trying to model, I think, is documents and news documents talking about certain topics. So they say, okay, so these documents link each other. So they explicitly model that relation. These two documents are similar because they're, similar in the content that they produce, and then what they talk about, right? So you can say like, well, if they link to each other, if the two documents link to the same document, they're likely to be similar. So these are kind of like relations that you can explicitly model in these frameworks. So we draw a lot of inspiration through these models, but the difference between what we're going to try to do in this is that this is always explicitly symbolic, right? So they don't leverage any type of neural net or neural representation. They just basically, model all the factor graph, all the facts that they have, and then they, have a single weight for all of these rules and try to learn, how to score decisions. On the other side of the aisle, when we go to like purely neural stuff, we talk about things like node embeddings and graph neural networks. I don't know how familiar you are with these things, but it's just basically, trying to learn or embed in a neural space things that are kind of symbolic, right? So a graph, think about a graph. It's symbolic in the sense that, what you represent the nodes, you represent the connection between those nodes, but then you're going to try to embed this in like a distributed space to learn a vector that represents things. So similar to language models, where you want to have words that have similar meanings being closed in the embedding space. Here, they're going to go to the notions of, two nodes that are similar are going to be closer in the embedding space. What does it mean that two nodes are similar? It depends maybe on their topology, what kind of things they're linked to, whether they have a label, and so on. So there's a lot of work in this area on trying to embed nodes with textual properties. So let's say if I have a node and that node is associated to some text, there's work on trying to embed both the graph and the text. There's what they call knowledge graph embedding, where they have graphs that are multi-relational. So basically edges have types and edges represent particular relationships. So things like we saw in the previous slide, similar, talks about sports, all of these things would be embedded. And then graph neural nets that try to go beyond pairs-wide relations and embed the whole graph. So the idea is that the context would be richer and each representation would be informed by the wider graph. So if this is something that you're interested, let me know. I can give you tons of pointers to this type of work, and it's a very active area of research. And then there's the neural-symbolic approaches, right? We're not the only ones looking at this type of problems. There's a lot of people looking into this, and I was able to kind of characterize the work around this topic into this 6 kind of like general areas. There are the people that work on using rules just as a way to specify how to build neural nets. So they just use rules as a way to kind of have a principal way to design neural nets, but that's about it. So a rule will translate directly to a neural architecture, and that would still be trained like any neural architecture would be trained. That's one type of work. There's other work that looks at differentiable inference. So when I say inference, this probabilistic inference, it's, let's say, trying to score all the, what's the most likely world in all the possible worlds. If you look at this from a traditional like computer science point of view, these are like very expensive problems, right? So they're usually sometimes NP hard, they can't be solved. They're worked in approximations and so on. And there's certain people that are working on how can we define this type of inferences in a fully differentiable way so that we can train them end to end like we would train a neural net. That's one active area of research. Then there is what we call rule induction from data. This is basically trying to learn new rules from a given knowledge base. So kind of like the example that I gave of Socrates is mortal, all people are, Socrates is a person, all people are mortal, then Socrates is mortal. They have this new knowledge graph where they have all of these things, and they're going to try to kind of like create new rules that aren't absurd. And then the two last 2 points is more where my work is situated, which is, try to find a way to combine DIP classifiers with probabilistic inference and specifically applying it to NLP problems, right? So a lot of this work, while it seems that it would be very general, when you look into it, sometimes it can't really be applied to natural language. For example, there's a lot of work on rule induction from knowledge bases, but they assume that we know exactly what are all the nodes, what are all the entities and all the relations in the knowledge graph, and all of them are symbolic. So each of them have, a name, and that's it. So we're not dealing with, oh, I have this paragraph, and this paragraph is, what do I do with that, right? How do I decompose it into symbolic components? So we're going to look into the challenges that are particular to NLP problems. I don't know if to go into this, but this is kind of like some of the work in these areas, into this particular types of, research areas, and some of the frameworks that are out there. In case someone's interested, they can like come back and look into this. And I try to kind of characterize the type of features or things that they provide. So whether they can deal with symbolic inputs, whether they can deal with raw inputs. With raw inputs, I mean open text or a vector or some like arbitrary feature space, whether they're declarative so that you can like go there and play with the system in a way that you can declare your own problems, whether they perform some sort of probabilistic or logic inference, whether there's rule induction, that on the symbolic side of things. And then on the neural side of things, whether they can learn embeddings for symbols, if they're end-to-end neural, meaning they're only trained, by back propagating, there's no other steps. And well, do they retrain their underlying neural nets, whether they're architecture agnostic, can I use it with any type of neural architecture, and so on. So our framework is the last one down there, called Derail. And we try to cover most of these things. There's some things that we do not provide, like it's not end-to-end, for example, but we try to kind of cover most of these features. So the goals of this work, to kind of make it concrete, we are going to introduce a declarative language to specify relational problems using symbolic abstractions and logical rules. So relational problems means, well, I have one or two or more decisions that are interdependent. That makes it relational. And I want to be able to express it using symbols and using logic. Then we also want to be able to represent the atomic components of the problem using rich neural representations. So if I'm going to model, for example, abortion, or I'm going to model women, I'm going to model children, I want that to be tied to neural representations as well. And then we want to be able to integrate declarative inference into the learning process. So we are going to be doing this search in the space of possible outputs or possible assignments to learn decisions that are consistent. So, our world makes sense. All decisions that are interacting are taken into consideration. But then I also want to be able to improve my neural representation from this. So I not only want to pre-train neural models and then just use them to score my factors and then just work on the inference. I want there to be a communication between the two paradigms so that my neural representations start to, the underlying embedding changes to represent the kind of thing that I want to model. And I'm going to show some examples of the types of things that we do. And then we're going to evaluate this framework on a set of discourse tasks that deal with long text and structural dependencies. So the overview is that we present the Derail. It's a declarative framework to specify NLP tasks. So we're going to break down problems into domain-specific atomic components. This can be words, sentences, paragraphs, documents, arguments, concepts, you name it. The level of abstraction is depending on the problem. And then we're going to explicitly specify dependencies between them, their properties, and other contextualizing information. And we're going to have two ways of represent the dependencies: over the output variables in like a symbolic way, and over the neural representations by having what we call a shared embedding space. Basically, that some of the parameters are going to be shared so that different tasks kind of like shape that representation. So this is kind of what the array looks like. So you define a task by specifying a set of entities and relations. in this example that I'm going to show, I'm going to try to model a debate, right? So I have U is the user, T is the topic, and V is the user that is voting for something in this debate. So I have users, I have topics, I have voters, and then I have some relations. I have the relation debates. So this user is debating, participating in this topic, or does this user agree or disagree with this particular topic? So entities can be discrete or they can be attributed. So they can be discrete where they're just one thing. No, there is an ideology. I know that there's Republicans and there's Democrats, and that's about it. Or they can be attributed. So a user, right? A user can have tons of properties to them. So they can have an age, a gender, they have a political affiliation, and so on. Or documents, right? And then in the case, the attribute is what? Just the text that is there. And then decisions can be defined using rules in clausal form. So clausal form basically saying a conjunction of atoms implies an atom. So kind of this way, like predicate 1 and predicate 2 imply head. So I modeled two simple things here. For example, well, whether if a user debates a topic, I'm going to try to predict whether that user agrees with that topic. And in the second rule, I have that voter V agreed with a topic, and voter V voted for user U, making like I voted for the argument that they presented. So that means that user also agrees with that topic, right? So this is some relation that we know is going to hold or is likely to hold, and we can explicitly state it. This is kind of like the symbolic component, and this is one example, but you can model anything you want. So you can define any type of entity, any type of relation, and write down rules in this way to kind of capture the dependencies that you're interested in capturing. And then the neural component is that each rule template is going to be associated with a neural net and a feature function. So let's say that I'm saying, okay, so this rule 1, I'm going to associate it with this network. This network can be any network that you can think of to represent that. And then a feature function is the input to that network. So let's say, oh, the user is going to have some features and the topic is going to have some features. So let's say in the case of the user, it could be, as we talked, the gender, the age, any other information that they may have provided in their profiles. And then for the topic, it's the text. So it's like a sentence of what is the argument being debated. Things like, for example, should semi-automatic assault weapons, should they be banned or not? That can be a topic. And then we're gonna define, right, so we have the input layer, and then each input has its own feature representation. And then we're gonna define something that we call ReLNIDs, which is a shared relational embedding space. This is like a lot of fancy words, but what it basically means is that I'm gonna share some of these parameters. So think of each of these boxes as a neural net, and the parameters are shared every time that relation or that entity appears, right? So let's say here in the rule 1 and rule 2, we used users and we used topics, and in both cases, then the parameters are going to be reused. And then a rule layer that basically defines the factor function, like that we discussed, that is going to score the final weight of that rule. So each rule is going to have a weight, and that weight is going to be learned by a neural net, which we call the rule layer. So it's kind of this layered architecture where you have an input and you have a shared space where you embed entities and relations, and then you have a scoring function on top that takes everything that's on the left-hand side of the rule and outputs a score. So now I have a neural representation of my entities, of my relations, and I have a scoring function for a weight for each of these rules. And then finally, the neural-symbolic integration comes by adding what we call the structure inference layer on top of here. So now we have a factor graph that is defined by the rules that we wrote. And then the weight for each of these factors comes from the neural net. So what we're going to do is we're going to think about an inference procedure just as a box that you input this factor graph, and it gives you, the most likely assignment to the structure. And then we kind of like use that to learn from goal data that we have how to backpropagate back to all of our classifiers to tune these weights. So in previous work of like Markov logic networks that I showed you, they just learn a single weight, right? So they keep updating those weights to kind of like learn their factor graph. In our case, we keep updating our networks, and our networks are going to be what gives us the weight for that rule. So at the same time, we are learning the weights and also changing the parameters of the neural net to reflect those things. So I think I kind of like went a bit ahead of myself, but inputs are defined by grounding rules in data, right? So where does data comes from? It comes from some data that I have that I'm gonna model and then I'm gonna learn from. So let's say, well, I have some debates that I already observed. I know who's talking to who, I know who's taking what stance, who agrees with whom, and then I'm gonna learn from that data. The collection of groundings define the factor graph, and then global assignment is found by running an inference procedure or probabilistic procedure. I won't go into details into like what type of algorithms we use for that, but that's like also an active area of research. There's lots of algorithms that are used to find, marginal probabilities or the best scoring function in a set of solutions. A lot of them are approximate because this is a very expensive, like a computationally expensive problem. And in Derail, we provide a few of these implementations ad hoc, right? So you don't need to implement your algorithm. You just, by writing the rules, it will compile it and it will run the inference procedure for you. And then the global error is used to update all parameters. So I have what is the observed structure. I have what is my predictor structure, and this the same way you would learn a single neural net, you're gonna learn this like collection of neural nets, right? But the idea is that it's gonna learn not to make each decision on its own. It's gonna learn to make all decisions jointly. So if you were to learn this in isolation, the parameters might not reflect the things that kind of play well together, right? So if you learn it in this, like what we call this global way, then it's likely to perform better. And we're going to see if that's actually the case. And this is kind of like a real visual representation that I kind of came up with to kind of show kind of how this works. So we have this example that I showed you before. So we have, a politician, who she is, the party that she belongs to, what she's talking about, and then a bunch of symbols that comes from that we explicitly model. So let's say we're going to model the stance, the two possible stances, pro-choice and pro-life. We're going to model the user. We're going to model the text. Then the entities that are being mentioned, women, pro-women, women of color, Democratic Party, and then a bunch of relations that we might want to model there. So whether, are they talking about this issue in a negative or in a positive way? What types of entities they're mentioning? What is the stance that they're taken? And then there's an embedding space, which is, this kind of like neural space where things are embedded into vectors. So now we're going to have a vector representation for each of these symbols. And then we use this to score the weights that we fit into a symbolic inference procedure. So then we have a bunch of rules and then weights associated with these rules. And then there's this kind of like loop that goes into here where both things feed each other. So I learn from my symbolic model, I backpropagate back, the vectors of my symbols change and adapt, and then I go back and forth. And this is done with the objective of making better predictions based on some data that I can use to, train my model.
We have questions before you go on.
Yeah.
So first question in the chat is, what metrics are you using in the models to test model validity? So I guess, how do you evaluate the effectiveness of this architecture?
Well, so the metrics that we use, so the loss function is defined on how similar the predictive structure is to the goal structure. So let's say that I look at all assignments that go jointly, and then I see how many parts of that structure are correct. So the specific loss function is called structured Hinge loss, if you're interested in looking it up. So basically it quantifies how different a goal structure is from its predicted structure. It's very similar to the traditional Hinge loss, but kind of like moved to structures rather than a single class. So you're no longer predicting just a single value, right? Not, you don't have just one input true or false or one input class A, B, and C. You have a whole structure. So it's kind of like quantifying how two structures are close together. So that's what we use in the loss function. And as to how to evaluate it, then we look at individual predictions, right? So how well do you predict agreement in the case of debates, or how well you predict stance prediction, and all of this like interdependent decisions. So traditional metrics come into place: accuracy, F1, precision, depending on what you're looking for.
I have two questions myself also. First question is like, how do you, is there some level of subjectivity here when you make these embedding space and like the relationships between them? And number two, if you add a new entity, do you have to describe its relationship to all the other entities again?
Yeah, so there's a level of subjectivity because you're choosing what to model, right? So you're choosing which relations or which dependencies you're explicitly modeling, but then you're learning a weight for it, right? So you're gonna find that, you know, modeling, it's kind of like something to play with, right? So you're gonna find that, well, if you model this, is better than if you model this other thing. So you can kind of, as you go, test and decide what things are worth modeling. But at the other time, not all, you know, you're not committing to those things being predicted, right? You're learning a weight for it. So the idea is that there's some uncertainty to the things that you're modeling. So if you're saying like, well, two people that have the same ideology are likely to agree, that's not necessarily going to hold 100% true, right? You're going to learn a weight, and that weight might tell you, you know, 80%, 70%, depending on what your data can capture. So you do explicitly model this uncertainty. And as to entities, well, you also have the freedom as to how you connect that entity to the rest of the problem. But yeah, I mean, if you don't connect it, then that embedding will only be dependent on its own, right? So if you don't connect an entity to another decision, then you're not learning kind of like a global representation for that entity. It would only be based on whatever prediction you make for that particular entity. And that can happen, right? You can have some decisions that you keep isolated. So if you look at a graph, it would basically just a node that's not connected to anything, right? So whatever you learn from that, you learn in isolation. But if you connect it to another decision, then the dependency is going to start to matter.
So as long as I can connect an entity to some entities, the rest of the connections can also be inferred. Is that correct? Okay.
Correct. So basically you use one to infer the other, and vice versa, right? So some of them are going to be observed, some of them are going to be unobserved, some relations, and then they're all kind of like inform each other. So the idea is that you might make better decisions if you model the interdependency than if you model them in isolation. So let's take, for example, the debate case, right? So let's say that I have Harris and Pence. In this case, it's easy for us, right? But maybe not for a machine. So we have Harris and Pence talking to each other. But then I want to model their stance on the abortion issue. If I were to do it without any dependency, I would just model, okay, this is what Harris said, I'm going to predict the stance. This is what Pence said, I'm going to predict the stance. But then if I model, oh, these two people are in different parties, so that means they are going to have different stances, right? So then you add some dependency that is going to tell your model, well, you don't want to predict the same thing for these two people, right? Or you're going to capture that they're likely to have different stances. So that might inform your model and add some bias, so that you write some inductive bias into your model to say, oh, I need to push them in different directions. So then, or you pick up some patterns in the data. Oh, when people talk about abortion and they emphasize women of color, they're likely to be Democrats. When people talk about abortion and they emphasize children and morality and religion, then they're likely to be Republicans, right? So these are things that you can capture when modeled jointly, then can capture some like essence of the world that makes your model consider everything when it makes a decision. Does that make sense?
Yeah, thank you.
Yeah.
Can I
Yeah.
do have one comment here. So is this like incorporating prior knowledge into your system?
Correct.
Okay.
It's incorporating prior model, and then also in a way that captures the uncertainty of it. So you don't necessarily, you could say this is a hard constraint and I have to trust it always. And the model allows you to do that. So in that case, you won't learn a weight for it. You just assign it an infinite weight. So you're saying my model, every time these two things, so you can say every time a Democrat and a Republican debate, they're always going to have a different stance. And you couldn't force that. Or you could say the model, well, I'm not sure, but I think this might happen. And then you learn a weight for it. So you can do both things. But both things model knowledge of the world, right? It's some expectancy that those things are going to be related somehow. Yeah.
How would the model deal with like an unconventional stance? For example, a pro-life Democrat.
Well, that's what you would hope the kind of uncertainty captures, right? So in the end, you're going to have this tons of weight, tons of rules, and the rule is going to have a weight assigned to it. So you can think of the weight as a certainty factor. So let's say when I'm talking about Democrats and pro-life stance, my weight is likely going to be small. So you're going to say like, that's kind of like how much you can trust it, more or less. So it gives you obviously outliers. The idea here is to add inductive biases. So outliers are likely not going to go with the overall stance, but the idea that you make it weighted is that you can capture that uncertainty. So you don't necessarily need to commit to that decision. So the decision has some weight. And then let's say you have other things that you can model. So maybe you have a Democrat that is pro-life, but maybe that Democrat, if you look at their friend group, they're likely to have more Republican friends than other types of Democrats that are more, like more into the extreme side of the aisle, or they're likely going to have participated in these other debates. So you can model other things that kind of like help you shape the representation of that. So in a basic model, you might not capture it, but as you involve more and more context to the model, then you might be able to capture those cases.
Yeah, got it. So in a way, instead of just relying on more and more data and hoping that the data will capture these fringe cases, you're trying to capture them through different contexts by looking at different encodings or different features that might show you.
And you want to kind of like say, well, I know what this concept is and what I want to capture in this concept, and I can explicitly reason over it by adding like some knowledge of the world. And then it gives you kind of like the explainable part. So let's say that you find that Democrat that is pro-life and you accidentally predicted the wrong thing. And then you can look at the rules and the activations and kind of see why you made that decision, right? So you may be like, oh, I saw him talking about this entity and then it activated this rule, activated this other rule. So you can kind of understand your model. And then that way, maybe hopefully build better models. That's like one motivation for it.
Perfect. Thank you.
Any other questions? Okay. So I'm going to skip this next slides because this is more of like the kind of like how we do it, how we formalize the program behind it, how we solved it. So, I mean, it's here in case you're interested later. It's also in the paper. So, just let me know and I'm willing to share with you. And also, what kind of learning laws we use and so on. So I'm going to move forward to kind of the analysis, unless, there's some objection to that and you want to look into the math. But if not, I'll go ahead with this. Any comments? Okay. So I'm going to show one of the evaluations that we did, which is what we call open domain stance prediction. We call it open domain because we are not necessarily looking at the issue, abortion, for example, pro-choice, pro-life. We're looking about maybe some claim that can diverge into that. So in this case, abortion should be illegal seems to pretty align with pro-choice, pro-life, but it could be, should abortion be legal after whatever weeks? It's like a more nuanced kind of like topic of discussion. So you need to kind of capture that too. And then we have users. Users participate in that debate. They have relations between them. So this is maybe, Facebook or some like social network where people, are friends with each other. And then you have this kind of like debate structure. So there are posts, people reply to this post, people reply to the replies, kind of like your standard political discussion in any social media platform. So we have these relations that we're going to model. We're going to model whether someone is pro or against a particular issue, where the issue is defined by a text expressing what the issue is. We have the authorship relation that we know. So we know which user is posting what post. We know who's responding to who. We're also going to assume that is known information. And then we're going to predict agreement. Agreement between posts, agreement between posts and claims, and agreement between user and posts, right?
Wait, sorry, Maria, before you move on, I got a direct message. Someone is interested in the math.
Oh, okay. Which part? The inference part, the learning part, the neural part, all of it?
I don't want to name the person in case
Yeah,
you're
sure,
not
sure.
Okay, so I'll go quickly over this. So so this is how we formalize the derail program. Because rules are written in clausal form, we can write them as linear inequalities corresponding to the disjunctive form. You know, so every conjunctions, implications can be written in their disjunction form, and then we can write them as linear inequalities. Here we have IR would be and you assume that each atom can either be negated or not negated, right? So we have the atoms that are not negated, the atoms that are negated, and then we can write linear inequalities in this form. So then each rule grounding defines the potential, and we can add it to what we call, well, a linear program, if we're familiar with that, which is basically an optimization program to be able to find, you know, the best assignment given a particular set of constraints. So weighted rules are added to the linear program with the weight that we learn, and unweighted rules are defined as hard constraints. So things that must always hold true. So then we can write this as an argmax problem, an optimization problem, which means I'm going to find the maximum assignment where each decision is binary. It's either true or false. So whether that atom is going to hold true or not. And each one has a weight, and then you have a set of constraints. The set of constraints come from the dependencies that you write, right? So you kind of can translate this to this problem. And this is how we define kind of like hard constraints. So this is what we call maximum posteriority inference procedure. And then what you're going to try to find is, you know, the assignment that maximizes the score, but that satisfies all the constraints.
Hi, thank you.
Yeah.
So that appears to be an integer program there.
Correct. It's an integral linear program. Correct.
And I know in theory those are supposed to be difficult to solve.
Yeah, they're difficult to solve, and you can we employ relaxations and approximations to be able to solve them. So you don't really have, if you were to solve the exact inference procedure, it's in theory NP-hard, right? So you can't solve it. But in practice, if your graph is not too large, you can do it. So it depends on, so what we do in the framework is we provide both exact inference and approximated. So depending on how large your problem is, you can either pay the price and use the exact inference, or use an approximation, and then you can do it faster.
And what complexity class did you say it belongs to?
NP-hard.
NP-hard, okay.
Yeah.
I just didn't hear you.
Yeah, NP-hard, but in theory, right? But in practice, let's say in the case of debates, if you only had a couple hundred posts, that's likely not going to be the case, right? So you can probably solve the inference in practice pretty fast. But then if you really want to model all the friendship graph of Facebook, then that's going to be impossible to solve, right? So in that case, you would want to use an approximate algorithm. We also have some other work if you're interested in kind of randomized inference procedures that we apply to this framework to kind of speed up this process. And we've got some pretty good results. So it's basically just something like greedy problems where we just randomly sample some things and then force the constraints on the output, and we found some really cool properties.
Thank you.
No problem. So this is on the inference side of things. And then the neural components is basically a scoring function over the set of parameters. So you have parameters for entities, parameters for relations, parameters for rules. And then every time the entity appears in a rule, you reuse the parameters. That's kind of like the idea that we have. That's what we call a shared embedding space. So basically you have tons of signal map to your embedding. So that way, you learn something that kind of captures all the aspects of your problem. That's kind of the intuition that we have behind that. So you learn relational patterns that contextualize the entities, and you capture properties that are unique to their types. This is simpler than it looks. It just basically means you just define one module for each of your entities, one module for each of your relations, and then you reuse them every time they appear. And then this, while simple and very related to work in multitask learning, if you're familiar with that, it's kind of like a principle multitask learning because we do it in a way that preserves the relations that we express in the problem. And we say that it gives you the possibilities to embed symbols and explain data, because then you're going to have one embedding for each symbol. So you can map your symbols back to a distributed space and vice versa. So it lets you do some cool things. We have some demo after to show you the kind of things that you can do. And then learning, we do it with these two types of losses, structure hinge loss, general CRF loss. These are very common in structure prediction, which is this idea of, predicting structures instead of particular outputs. And you need to, in the case of the hinge loss, you need to solve the inference procedure that we just discussed. So, this is where approximation methods come into place if you want to do it faster. And same for the CRF loss. I have all the details and some experiments with different loss functions in the paper if you're interested. But basically, the structure hinge loss is better, computationally speaking, because you can use approximate inference to approximate the solution pretty easily. Whereas the CRF loss, you need to approximate the partition function, which basically means enumerating all possible solutions in your solution space. And that is really expensive. But there are also, kind of approximations around it. And the one that we use is called keeping just a beam, like a subset of possible solutions, and then just marginalize over that. Any questions? Okay. So back to this problem. So just to kind of like remind us, we have posts, we have users, we have topics, and we have these relations. The author and the respond relation we're going to assume is known, and the agreement and is pro relations we're going to predict. So the evaluation plan is that we're going to test different modeling strategies to see which parts of our framework are being useful for modeling these types of problems. So the first one we're going to do is what we call local versus global learning. So this is what I've been telling you, right? Local basically means I'm going to have one single neural net for each of these interdependent decisions, and I'm going to apply no inference whatsoever to learn them. So I learn them independent of each other, and then I just use them to predict. And global learning is when I use this whole pipeline to learn things that go well together and use the global losses. We're going to try RelNets, which means what is the impact of sharing the parameters or of having like encoders that are shared. So using the same parameters to model the entity every time it appears. And then modularity basically means what do I gain by breaking down the problem into components rather than just saying, oh, this is all my input, I put it all as a single feature and try to predict it. And then am I really learning meaningful embeddings, right? So I model these concepts, I learn some embedding for these concepts. Is there some signal there, right? Can I like get something from these representations? And is my model really interpretable? So I am going to use this set of baselines. I'm going to compare it to end-to-end neural nets. So basically, features, single prediction to model agreement, and stance prediction. Then I'm going to compare it with relational embedding methods. So if you remember at the beginning of the talk, I talked about graph neural nets and knowledge bases and so on. So I use some of those methods to model this. Those are purely embedded. So I'm going to compare against those. And then I'm also going to compare to other probabilistic logics, so other symbolic methods. I'm going to compare to two, one that is purely symbolic and another one that is also neural-symbolic as ours, and see if we get some edge. So this is kind of like the results that I have on domain stance prediction. So to kind of parse this, P means post. So how good am I at predicting the stance of a post? U means user. So how good I am at predicting the stance of a user. B is user, but a user that votes. So how good I am at predicting the stance of a voter. The main difference between user and voter is that user produces text while the voter doesn't. So I have less signal for that. And I have two setups. I'm going to call one random, one hard. Random means that I just took a bunch of debates and I randomly sampled train, dev, test, this is, I think it's tenfold cross validation. So I have 10 folds, trained with 9, test with 1. I did it 10 times and then averaged. In the random case, all these folds are drawn at random. And in the hard case, what I'm going to do is I'm going to push things that talk about similar topics to different folds. And this is a harder setup because different topics that talk about abortion, different topics that talk about guns are going to be put in different folds. So basically, I'm not going to have seen similar topics when I learned. So it is a harder problem. And obviously, the numbers are a little lower. Then here, the models right here, local means the ones that I just used a neural net to predict, no inference at all. The relational embedding is this kind of like graph embedding, relational embedding type works that put these things in a graph and then learn to embed them. Then I have the probabilistic logics is the symbolic, PSL is purely symbolic, TensorLog is neural-symbolic, and then derail is my framework. And these are the different types of things that I did. So joint inference means I train locally, predict globally. Global means I train globally, predicted globally. So that means whether the inference is used during learning or not. And then RelNet is, what's the impact of also adding the parameter sharing component. And I found that all of the things help, right? Inference helps a prediction time. It helps even better if you use it during training. And it's even better if you share parameters. And that kind of like happen across folds. And those are the results that I have for that. This is macro F1, but it would be, I think the classes are pretty balanced. So we have almost the same amount of pro and con. Any questions in this? This is just kind of like, showing the numbers that we had. And then this is maybe more interesting, which is to kind of like some qualitative analysis to look at what actually happens. So I talked about this idea that now I have symbols, I have scores for the symbols, and I also have embeddings for the symbols, right? So I'm gonna take the issue of guns, I'm gonna look at some debate statements, and I'm gonna look at the scores that are given to them for these other symbols which represent ideologies. So we have conservatives, we have libertarian, we have moderate, we have liberal, and we have progressive. And then we have the statements. So we have kind of like statements that talk about not passing any type of gun control or gun control being ineffective to have higher scores for conservative and libertarian symbols. And then things that talk about pretty like some like form of gun control are even like banning most guns, confiscating guns, and then having really high scores for liberal and progressive symbols. And then you got moderates kind of like in the middle here with statements that are a bit less strong. So things like gun control might be good for society, but then you see, that kind of like the weight is a bit less pronounced, right? So it's even spread more across topics. So this is me not to answer your question about, this like, how do you capture these people that don't necessarily match what you're expecting to? You would expect their symbols, their weights to be more spread out across the different classes rather than, kind of like basically here, the full mass is taken up by the left-leaning symbols. And the other thing that we did was, well, this is mapping text to symbol, but what about mapping symbols to text, right? Text is an embedding. So we have a vector that represents what is this text. And we're going to try to see what is the symbol. So we have an embedding for symbol. We have an embedding for text. And we're going to see which ones are the closest together in the embedding space. So basically taking something like a cosine similarity metric over the vectors that we learn and see what things are being closed in this space. So we find that the embedding learned for something like liberal in the context of LGBT issues is very close to statements talking about gay marriage ought to be legalized, should be fairly legal. And then we find that the conservative symbol was closer to, it was more diverse, So you would have things that would be both pro or con gay marriage, but they all have mentions to either some moral aspect or some religious aspect. So you could, capture this type of thing. So while it not necessarily translate to the stance itself, it did translate maybe to the type of framing that they use to put this, kind of like put this arguments forward. And then you can actually go back and look into this, right? So I say, I have this symbol. I want to see why I learned with this embedding. Does it make sense? And it lets you kind of visualize your model a little bit and kind of see what's under the hood, because you can map it to symbols that you know what they mean. Any questions here? Okay. And then we did one final qualitative analysis, and we say, okay, that makes sense, but that was our training, sorry, our data sample from the same training distribution, right? So it was all these debates that we used to learn. So we were able to capture some good things there. What would happen if we were to take other domain data coming from somewhere else, but that models the same kind of topics? Can we use this model to see what's going on there? So we downloaded statements made by 3 prominent politicians from ontheissues.org. So this is a webpage that kind of collects what politicians say. And we try to classify their statements with our model. So we had Sanders, Biden, and Trump talking about guns and abortion and other topics. So on the left-hand side, what we did was kind of like plot kind of like the weights, that the symbols got. So in the case of, and the symbols being their kind of like political leaning. So we found statements for Trump were, kind of like more heavily leaning right, than Sanders more heavily leaning left, and Biden leaning left, but less so than Sanders. So we could kind of recover the political spectrum of these candidates based on their statements and the symbols and the embeddings that we learned for our symbols. And then also we here looked at some of these actual statements that they make and the label that we were able to map for them with our model. So we were able to count some like interesting cases. For example, in the case of Trump talking about abortion, we did see some, if you see this is not fully read, right? So we got some left-leaning things there. Some of them are errors and noise, but other of them were actually things that seem to be correct. For example, statements that Trump made in the past about, Planned Parenthood does great work in women's health, seems something that, a statement that is more likely to be associated with a Democrat, and our model did pick it up as one. So we were able to kind of like capture this kind of things. And that's kind of like the last result I have for you guys, and kind of a short summary of what I tried to do with this was motivate the need for a neural-symbolic approach that can be applied to NLP tasks involving long text and contextualizing information, and why that matters and why that would be helpful, and introduce a general framework to support this, which is what we've been working on here, and demonstrated this flexibility. So I showed you just one example. In the paper, we used 2 other tasks, if you're interested in taking a look. So we also try to recover argument structures from essays written in things like the TOEFL, that they make you write this essay on particular topics. And we were, had a task where you identify claims and support messages for those claims. That's what all the other tasks. And then another domain similar to this political stuff. And then we obtain models that are easy to interpret and expand, right? So we have the symbols, we have the rules, and we kind of see that, we are learning something that makes sense, and we can easily expand this, add other rules, model other concepts to enrich our models. And that's basically what I have for today. So I'm open to more questions if there are.
We have a question in the, first of all, thanks for the talk. It's very interesting. We do have a question in the chat.
Yeah.
Ricardo is asking, could these models be used to detect bias from a particular source, such as ethnic groups or geographical regions?
We are actually